Good afternoon and welcome to a new Adevinta Meetup, this time online again. Today we will talk about machine learning. We will have two talks. The first one by Ana Solaguren-Beascoa from BenevolentAI. She will talk about machine learning solutions in the drug industry, in the drug discovery industry. And then myself, I will present some machine learning solutions related with SEO improvement that we do in InfoJobs, that is part of Adevinta Spain. But before starting with the machine learning, let me introduce you to Clara. She is a colleague of mine of the people team in Adevinta Spain. She will talk about the company and our project, and we hope you like what she presents. So Clara, when you're ready.
Thank you, Didac. So welcome, everyone. As Didac told you, I would like to introduce you who we are as a Adevinta company. So basically, Adevinta is a global online classified specialist operating digital marketplaces in 12 countries. And as you can see in the slide, we are a global digital player and the biggest marketplace specialist in Europe. But apart from that, we are still a family of local brands. Here in Spain, we are a small family of marketplaces, and we're based in Barcelona. And our main purpose is to help people to find they need in the key moments of their lives through our brands like Fotocasa, Apitaclia, InfoJobs, Coches.net, Motors.net, and Anuncios. And together we reach almost 18 million active users each month, which is a lot. Currently, now in Adevinta Spain, we are looking for a data scientist for our InfoJobs team. So if you have background in data science, projects with focus on predictive modeling, machine learning, deep learning, NLP, speech processing, and so on, and you are interested in knowing a little bit more of that, so you can contact me by LinkedIn in Clara Chufraluna. You have here my name in the slide, or you have the link to the job description directly to apply to this job. Didac.
Thank you, Clara. Sorry, I didn't introduce myself at the beginning of the talk. My name is Didac Fortuny. I am data scientist in Adevinta Spain, and as I told you, I will give the second talk. But first, the first talk will be by Ana Solaguren-Beascoa. She has a PhD in physics, and she has been working as a data scientist for several companies in London for the last years. She's also a good friend of mine, and she will talk about her current job in the drug discovery industry. So, Anna, when you're ready, you can start. Thank you.
Thank you, Didac. Okay, so hopefully you can see my slides and my pointer. So yeah, what I'm going to present today is the work that we are doing at BenevolentAI in order to improve the process of drug discovery. So drug discovery is mainly like the research process that pharma companies need to do before they put a new drug into the market. So traditional drug discovery has to face different challenges. The first part would be the price that they have to pay in order to develop a new drug. So it's quite costly to put a new drug into the market. It usually takes an average of around $4 billion to develop a new drug. Also, it's usually quite a risky business, given that it's around or more than 88% of the drug programs fail. It also takes over 12 years to put an idea, so from the moment that it takes to put an idea to the market, if it's ever productionized. And also, all of this has a strong societal cost. So we know that out of the 10 top-selling drugs, we know that they're affecting on less than 50% of the patients. And there's still around 20,000 diseases that have no effective treatment. Sorry. Of course, we can see this as a world of opportunities. So as I just mentioned, there's around 20,000 diseases that have no effective treatment. But we know that we have around 4,000 drugs, so that would correspond to 4,000 different molecules, out of a space of around between 10 to the 20 to 10 to the 60 molecules. So there's a large space to find new drugs that could be effective to cure or at least palliate some of these untreatable diseases. From a biological perspective, we also know that we can still target around 20,000 genes to cure or at least palliate some of these diseases. So what do we do at Benevolent? Benevolent is, I broke here Benevolent in 4 different areas. First, we have the area of the knowledge graph and all of the machine learning or AI models that we build in order to speed up and get a better performance of the research that we do, like in drug discovery. We collaborate with scientists that try to drive all of the machine learning models that we build with some scientific background and try to put context to the models that we're trying to build. Once we have all of the knowledge in place, we actually have some labs in Cambridge where we can test hypotheses about diseases, and also where we can actually create and test whether new medicines that we predict or new molecules that we predict that might be useful for to treat a disease actually work. So how do we work together? BenevolentAI is broken into 4 different product areas that I'll explain a bit in more detail later. Each product area is broken into different teams, and each one of the teams has a variety of people working together, mainly scientists and tech people. So, for instance, we usually have AI scientists working together with data scientists, engineers, and depending on the team, we will have bioinformaticians, chemoinformaticians, and also drug discoverers that will help us understand all of the science that we're building our platform around. So these are the 4 product areas that I was talking about that build up the Benevolent platform. So in my case, I'm specialized in the part of molecular design. I've been 9 months working with a chemistry team, but I'll briefly explain the other 3 areas too. So the first piece of the Benevolent platform is the knowledge piece. So this is where we try to understand which are the right foundations from a biological point of view, from a chemical point of view. So the knowledge piece of the company is built by a knowledge graph. How does this knowledge graph work? So we know that we have a bunch of open source biomedical databases, and we also have access to scientific papers that have large amount of information from biomedical and chemical sources, right? So we can grab this, in the case of like databases, this would be the structured data and unstructured data coming from the scientific papers, and try to extract as much information as we can in order to put it into a knowledge graph. So what are the benefits of having it in a knowledge graph? It's impossible for a human to go and read all of the scientific papers and try to prioritize and extract correlations between diseases and a drug, genes and a drug, and so on. So the easiest way is to build a knowledge graph and allow experts to look into the knowledge graph and prioritize and understand correlations between entities. So for instance, here in the right side, we have an example of a tiny, tiny piece of what could be the knowledge graph. So let's assume that we would be interested in looking for a drug that could be related to ALS. In the knowledge graph, we would go and search for ALS that would be connected to the entity. So it would be, we would know that it's a motor neuron disease. This motor neuron disease, also from the literature, this entity correlation is extracted, and we know that it's a neurodegenerative disease that is somewhat connected to some kind of generic information that might be connected to a drug that could be useful for ALS. So how does this kind of relation between entities, how is it extracted, right? So this is extracted from the context. We have NLP models, natural language processing models, that try to understand these relationships extract these relationship from the literature. So for instance, here I show two examples. On the top part, we have a positive relationship that would be, for instance, in this case, SOD1 mutation corrects ALS phenotype in human MNS. I can tell you that SOD1 is a gene and ALS is a disease. And from this sentence, our machine learning models actually understand that there's a correlation between these two entities. And they can, and then it extracts these connections and it adds it to the graph. What happens? That also ALS might be connected to other entities within the graph, and also SOD1 might be connected to other entities within the graph. And in this way, it simplifies the way that we can actually connect information entities, for instance, ALS in this case, to other information that might be connected to important genetical information. Of course, our models have to be smart enough in order to understand whether there's a negative or an inconclusive relationship. So for instance, in the bottom sentence, we actually see the example of an inconclusive relationship. So for instance, let's say a researcher investigating SOD1 is suffering from ALS. In this case, there's no obvious relationship, and therefore a natural language processing models will understand that there's no relationship and will not add this connection to the graph. The second part of the platform is where we try to understand which is the right target that we have to tackle in order to cure a disease. So I will be talking about proteins in this case, in most of the cases. It's not always a protein, but just to simplify, these are proteins in the body that are the responsibles for a particular disease. And we have maybe to connect or disconnect some parts of the protein in order to cure or at least treat a particular disease. So this part of the platform is the part that tries to understand which is the right target that we have to look into. The workflow is a bit complex, but I'll do my best to simplify it. So we start from the knowledge graph, as I explained earlier. This correlates different entities between each other, builds this relationship. We can then go to the interested piece of the knowledge graph, and experts will actually extract all of this information, curate this data, and expand this data as they think is important. Once this process is finalized, we will end up with a disease data package. This disease data package is then used to train our models, and this can be models that can be as simple as a human SQL query, or up to something as complex as reinforcement learning, depending on the type of project that we're working in. And using an iterative process, we actually then grab these models, have some predictions, and then have a leaderboard evaluation. So this would be like evaluating our model with some metrics, or even have some experts looking into the model predictions. And this is an iterative process. And once we're happy with how our models are performing, then we can extract a predictions package. This predictions package will allow us to triage a bunch of hypotheses. So what will this do exactly? In this case, we would have a list of targets, and our models would predict, for instance, a score for each one of the targets. And this would allow us, with some experts' help, to triage some predictions and then choose the most interesting targets that we think could be related to a particular disease. Once these targets are selected, then we end up with an hypothesis package. And this hypothesis package is then used to take it into the lab and check whether that target actually is related to a disease or not. And we will end up with a validated hypothesis package. The third part of the platform is the part of precision medicine. So this is where we try to understand which is the right drug for the right patient, right? Not all patients behave in the same way. So how can we understand the subgroups of patients for a particular disease? So what the pipeline does, it tries to identify subgroups of patients and distinguish the different biological mechanisms that they have to deal with that disease, right? So for instance, here we see a plot, a schema that would, in the x-axis, what we would be seeing is some type of biological information from patients. So each square would belong to a patient. That could be, for instance, some biological information from a piece of tissue for a particular disease. And then on the y-axis, what we see is how this disease changes or is expressed on each gene. So we have a list of each box would correspond to a different gene for each patient. And how does this disease, how does this gene look for each patient, right? Then what we can go is to try to understand a particular method of a disease. So for instance, if we look at diabetes, we know that diabetes can be like the method, how a patient, a biological reasoning why a patient gets diabetes might be different for different patients. So let's choose method 1, let's say for a particular disease, and we choose all of the patients that have that disease given that method, right? So once we choose these patients, using machine learning, what we try to understand is, given the patients that have this disease given mechanism 1, which are the subgroup of patients given this biological versus genetic information, right? And you actually see that there's different patients with which are part of different subgroups. And this is how we detect different subgroups of patients for a particular disease. And it makes it easier then to tackle or give the right medicine to that patient, understanding much better the biological mechanism behind that disease for that patient. The final part of the platform, now that we understand the diseases, we understand which is the protein that we have to tackle for that disease. We understand the subgroups of patients that we have for a particular disease. Now we have to find the right drug. So first of all, I wanted to present a bit how we translate the information of molecules into vectors. So a molecule usually is the key part of a drug, right? What will cure or treat a disease. So we need to transform somehow the information that we have of a molecule into a vector in such a way that our machine learning models will be able to ingest this data and be trained. So on the left-hand side, I show the graph-based type of encoding. So what this does, it encodes the neighborhood of the atom. So what we look is at a particular atom and start looking at the radius around it. And then look at the substructure of that particular area. Then once we see this substructure, we go to the vector and we know that this particular position in the vector corresponds to that substructure. So we're going to put a 1 there. Then we open the radius and we see that there's another substructure that is present. And we go to the particular part of the vector that corresponds to that substructure, and we put a 1 there. So we end up with an encoding of that molecule, which corresponds to a vector full of 1s and 0s, right? The second way that we can actually encode a vector is by it is the feature-based encoding. So this works a bit similar to NLP, where you have a dictionary of words, and then you go into a sentence, and then you count how many times does the word and appear, right? And then once, if the word and corresponds to position 0, you put, and it appears 3 times, you put a 3 in there, for instance. So this does something similar. It grabs a molecule and it breaks it into chunks, and its different piece corresponds to a different word, let's say, right? A different position in the vector. So for instance, in this case, we see this red area, this red substructure that corresponds to the first position in the vector, and it appears just once, so we would put a 1 here. Then we would have other pieces, other substructures that would correspond to other positions in the vectors. We would count them and put the corresponding number in there. So this is how we transform the two ways of transforming molecules into vectors that then can be ingested by machine learning models. But so this is a nice picture, right? But then one of the problems that we have in chemistry is that the chemical space is extremely large. So as I presented at the beginning, the chemical space, so the molecular space, is around between 10 to the 20 to 10 to the 60 of molecules are estimated to exist. And just as a reference of numbers, the universe is around 10 to the 22 seconds old. So it's a large number of molecules, which means that if we have to find the right drug within such a big pool of compounds, we need really good, effective search algorithms to do so. For that, one of the mechanisms that we have to do that is virtual screening. Virtual screening, well, let me start with, usually in a problem, trying to find a drug, what you have is a pool of compounds that could go from a handful. If you, for instance, look at the compounds that a vendor can, are available from a particular vendor, or 10 to the 6 if you're just looking to all of the possible compounds in nature. So what we're interested is to find what we call hits. Hits are the molecules that have a list of properties. For instance, they have to be potent against a target. So they have to actually connect or disconnect the interesting part of the protein for that disease, right? We want them to be stable. We don't want to ingest that drug and that then it explodes in our body. We want it not to be toxic. So we have to look at toxicity. We want to ingest a drug that we know it's not going to kill us. And there's other biological properties, such as, for instance, brain permeability. We want to protect the brain from any drug that we ingest, except if it's a brain type of drug. And a list of other biological properties that it has to fulfill. But on top of all of this, it also has to be novel. Because if you end up finding a drug that has all of the interesting properties that I just mentioned and some other biological properties, but then it's a drug that has already been patented, you cannot really make money out of that. You've just wasted all of your time and resources to find that drug. So I will be calling hit. So we know a hit as the definition of a compound that will fulfill all of these properties. So out of our pool of compounds, we usually have randomly distributed hits within the pool. So what we want is to actually get to detect as many hits as possible. So the perfect world would be this middle picture, where given that in the lab we are limited, we have limited resources, so you cannot just grab 100,000 compounds and test if they are active or they have the most interesting properties. You have to choose a small number of compounds and look if they're actually interesting or not. So you're limited to have like a top N compounds that will be screened, and we want those to be the most interesting ones. So in the perfect world, out of the top n screened ones, we would have the top most interesting ones, the perfect hits at the top, right? When we would be ranking them. So usually we go from the random pool of distributed hits to a perfect ranking of hits using machine learning models or some chemical filters and selection strategies. Of course, in reality, you never have the top perfect compounds on your top n screened compounds. You usually have a mix of hits and non-hits. And what you want to get is as close as possible to the perfect ranking, so that the ones at the top of them are as the most interesting ones, and you have as little non-hits as possible in your top n compounds that are the ones that you're going to actually test in the lab. So how virtual screening works is as follows. So we know that we want to tackle a target X, that would be a protein, right? Then we go to the literature and we find compounds that we know that are inhibitors, if we want to inhibit something from that protein, from this target, and that are selective of targets. So we want it to be inhibit on that protein, but not touch the other proteins in the body. So we choose some of the compounds from the literature, and we use this as the seeds of what we will call hit identification. Using this compound, we will then do some similarity searches for new compounds, and we will end up with a massive pool of compounds that are similar to each one of our seeds. And then out of this pool of compounds, we will use machine learning or 3D techniques to select the ones that we think are the most interesting compounds to then test in the lab. Then what we do is go and test it in the lab and see which ones are actually interesting hits, which are hits and which are non-interesting compounds. So in this case, for instance, I show the green blobs that would correspond to hits, and the orange blobs would correspond to compounds that have been tested in the lab and don't have the right properties. So the next step would be to select one of the hits or a bunch of hits and start the process again. Go to a pool of compounds, select the most similar compounds to this hit, to each one of the hits, use machine learning or 3D techniques to select the best compounds, and then go and test them in the lab. So in this way, what we do is we end up with a pool of drugs that are possible candidates for a particular target, and then study their chemical and biological properties and how they behave against off targets and the other properties that I listed out, and decide which is the best drug candidate. So yeah, if you want to learn more, you can go to the Benevolent webpage where we have the list of publications from our team. And also I left here a bunch of papers if people are interested to look further into machine learning and drug discovery. So thank you.
Thank you, Ana. Now, if some of those who are looking to the video have a question, you can write it in the chat in YouTube. In the meantime, I have a question for you, Ana.
Yeah.
When you told that you were doing this virtual screening, that you selected a seed and then you looked for all the similar molecules that are similar to that seed, mm-hmm. How do you compare? You still have to compare all the big millions and billions of molecules against that seed.
Yes.
How do you do it?
Yeah, so chemoinformaticians there's libraries that help you do that, and chemoinformaticians take care of that, and we have tools that already do this that are available online that help you do this. There are also like techniques that are built in-house that are not necessarily using machine learning, but like chemical properties from the compounds that are used to prioritize which are the subgroup of compounds that will be the most interesting ones. But yeah, it's actually most of it. This is available open source.
Okay, and I don't know if there are questions in the. I don't think so yet. I have another question. I was wondering how many times do you end up with a good hit for your problem, or if there are the ratio between how many times you are successful and how many times you are not.
It depends a lot on the project too. So every time you have a different project, usually you end up building a new model because you're interested in a different compound space. And sometimes so for instance, if you're looking at a particular disease, the available data that is so we start with open source data, right? So for instance, we go to Campbell, that is an open source chemical library with chemical properties, and then you start training your models using Campbell. Sometimes there's projects which will have a lot of data and a lot of enriched information that will make us build a much better machine learning model, whereas in some cases that available data open source is not that good. So it depends on the project. You might end up with like a lot of hit identification. Also, there's different stages of the hits. There's then the hit expansion, and you start like making this bigger and bigger. So depending on the project and depending on the open source data available, for instance, if you start with the hit identifications, you might end up with a bunch of hits, and in some cases even with none.
Okay, thank you, Anna. We have another question by someone in the audience.
So at the beginning, you said that the usual development time of a drug was around 12 years. Is that time reduced applying AI techniques? Hopefully, yes. There's still, I don't think there is anyone who has productionized a full drug only using AI, but that's what we're working for at Benevolent. I do feel that some of the processes internally are being sped up, like they're speeded up. But again, I don't think there's a drug that has been put into the market that it has fully been developed with machine learning yet. So we're still building that. Also, do NLP algorithms of the knowledge graph automatically label the entities, or some level of human interaction is required for that? I don't work directly with the knowledge graph people, but I would assume that at the beginning there was some kind of labeling at the very beginning, right? I don't think now there is any type of direct human interaction, but of course this is an iterative process, and always in the knowledge graph there's improvements to be done. And I know now that there's a bit of work that needs a bit of manual labeling in order to optimize the way that the knowledge graph is built. So it's a bit of an iterative process, but right now the NLP that is used, I think, is not fully manually labeled.
Okay, thank you very much, Anna. If someone in the audience has more questions, we can continue the conversation at the end of the talk, after my talk. Thank you very much.
Thank you.
And now the second talk, I will talk about how in InfoJobs we use machine learning to improve the SEO of our web page. Yes, at the beginning, for those of you that don't know what is SEO, I will explain it, and I also will explain very fast how can you boost the SEO of your web page. Also, I will present how we did this project, the roadmap that we followed. Then I will go to the particular machine learning techniques that we used, and I will show how the solution implemented looks in the real world. And finally, I will talk a bit about the impact of this solution. Okay, SEO is nothing more than, well, SEO, search engine optimization, is nothing more than the set of techniques that you can use to improve the position in which your web page appears in the results of any search engine, without, well, taking into account that the first spots are usually associated with paid advertising. Increasing the SEO, increasing the visibility of your web page in the in the results of the search engine pages has a clear impact on the quantity, but also the quality of the traffic that your website will get. There are a lot of ways of improving the SEO. I will just present the more popular ones. First, you can edit the contents of your website or add new contents because you are interested that your website is updated and is relevant for the general public. If your website is updated, the search engines will like your page and will give you relevance, good relevance. Then you can also modify the HTML tags that are present in the source code of your website, because with these HTML tags, you can tell the search engine which parts of the website are more relevant, and this also can give you better results in the search engine. Then you can also promote your site to appear in other popular sites. If a search engine sees that your website has been linked from popular websites, the search engine will understand that your site is also popular, so it will give you relevance. And finally, you can create a network of internal links between the different sections of your website in such a way that the page rank of these pages is transferred between ones and others. The page rank is nothing more than the relevance algorithm that Google uses to sort the results of the search engine. In InfoJobs, we saw that with machine learning, we could easily go for this last point and have very good results with not so much effort. So we decided to go for it. And we wrote this goal here. We wanted to generate a structure of internal links in the InfoJobs search page in such a way that when someone looks for a keyword, we can provide them links to the results of similar searches. For example, if someone looks for a Java developer in the search page of InfoJobs, we will give them links to the results of other searches, similar searches like PHP developer, backend developer, etc. This has been done in the past for lots of years and in a lot of places. The point of our solution is that we have built a model that is intelligent enough to understand what the person is looking for and return automatically keywords that are similar to that and that are interesting also for the same person that looked for the original search. This is what our machine learning model has added. So to go for this goal, what we did was start extracting data with, this roadmap is nothing that we have invented. It's the roadmap of a classical data science project. We started the data extraction with the help of the SEO expert of the company, the marketing expert of InfoJobs, and also the data analysis team of InfoJobs. Then this is when the data science team entered the project. We built this model that generates automatically this net of internal links. And then once the solution was implemented or the model was created, the solution had to be implemented in the backend by the backend team. Also, how the links look like had to be designed by the UX design team and implemented by the front-end team. And the SEO expert was the one that was monitoring that everything was working well and that the solution was indeed having the result that we expected. And the whole team then worked for checking that the solution was working and also designing future iterations to improve the solution in the future. I will focus only on the second point because this is where the machine learning is applied. One second. Okay, from all the machine learning techniques, there is a subset of techniques that work with natural language processing, like the ones that Ana presented in the previous talk that created the graph. These techniques, we say that they are working with natural language processing. These are the techniques that work with text mainly. Of all the techniques, the machine learning techniques for natural language processing, there is a popular set of techniques that are called word embeddings. These word embeddings are nothing more than models that transform words or sentences, at the end concepts or keywords, you can say it as you want, these keywords into vectors like this, into vectors of any number of dimensions. Here I have only printed 6 dimensions, but you could end up with vectors of the number of dimensions you want. The point of these word embeddings is that 2 words that have similar meaning will end up in points of the multidimensional space that are close to each other. For example, truck driver and van driver, because they have similar meaning, they will end up in points that are close to each other. I have only plotted here 2 dimensions because I'm not able to plot 6 dimensions in PowerPoint, but the idea is the same. 2 vectors that have similar meaning will end up close to each other. Then the hotel receptionist and the spa receptionist, the second example, will end up also close to each other and far from the drivers because the meaning is not close. And finally, the veterinarian will also be separated from the other groups because the meaning is not similar. Then it is easy to understand that when we have a new keyword, like pool receptionist, if we use the same model to calculate the vector, we will find that it's close to other keywords of our pool of keywords. In this case, we will find that if we want keywords close to pool receptionist, we will have spa receptionist and hotel receptionist that in this multidimensional space are close to the new keyword. Having this word embeddings framework in mind, we have used 3 particular models. The first one, a pre-trained language model. This model was created by the community, is available online for all the machine learning practitioners that want to use it, and it was trained with millions and millions of Wikipedia articles. The good point of this model is that, as I told you, it captures the meaning of the word, so the semantic relationships are well captured. Van and truck here would end up being close because both are vehicles used for transporting things. But we found some bad points of this model. The first one, we found unexpected semantic relationships. With this, I mean that, for example, Java, in the context of InfoJobs, is usually the programming language. We have people who is looking for a job and they know Java, so they put this in the resume. So when we look for concepts that are close to Java, we would expect to find other programming language or at least engineering skills. But what we find is Sumatra, because both Java and Sumatra are islands in Indonesia, and using the general knowledge of Wikipedia, Java is more associated to the Indonesian island than to the programming language. This was one of the problems of this general model. And the second problem was that concepts that are not semantically related but could be interesting for the same users in InfoJobs end up separated. For example, delivery person in Caudete and checker in Caudete both have different job titles, so it's not incorrect that they are separated. But maybe in Caudete, that it's a small town, the person who is looking for a job of delivery is also interested in a job as a checker. So we would like these 2 concepts to appear close because even though the meaning is not the same, they are interesting for the same InfoJobs users. Then what we did was create our own model. We used all the text that we have in InfoJobs. In InfoJobs, we have a lot of text because we have all the offers that the companies publish in our website and all the resumes of the job seekers that are there looking for a job. We use all this text to create our own language model. Then, with this new model, we succeeded in the first problem that we had with the previous model. Now, the closest concept that is closest to Java is PHP, that is another programming language. And track and ban are still close because the meaning is still the same. The problem with this second model is that because we used less data to train it, because I told you that in InfoJobs we have plenty of text and plenty of data, but not as much text as in the whole Wikipedia. So because it was trained with less data, the overall performance of the model is a little bit worse, is slightly worse. And then we decided to train a third model. And this model was a bit different. It was not based on the meaning of the words, but in the behavior of the users of InfoJobs. I will explain it with an example. If a lot of InfoJobs users has looked for both builder in Girona and builder in Figueras keywords, if a lot of users has looked for these two keywords, they will appear close in this multidimensional space. And if few users have looked for builder in Girona and builder in Caudete, even though the meaning is quite similar because both of them are builders, if there are just a few users that have looked for the both concepts, they will end up separated. And on the contrary, if builder in Caudete and plumber in Caudete are looked for by the same people, because again, Caudete is a small town, so maybe the person who's working as a builder is also working as a plumber, they will end up close, even though the meaning is not the same. This model is more focused on what our users are doing. But the negative point of this model is that we only can vectorize searches that has been previously done in the past. If someone writes a keyword that has never been seen in the past, we cannot associate a vector because we don't know which are the concepts that would end up close to it. To sum up, with these three models, we designed this final algorithm. When a new search appears, like this, Java developer, first, we use the third model, the behavioral model, and we vectorize this new search. We vectorize all the searches, the pool of searches that we have in our history in the database, and we return those that are close enough to the new search based on a threshold that has been defined using analysis. If we don't have enough results that are close enough to the new one, we use the other two models combined to find keywords that are semantically similar to those to the new one, and we complete the list of results. In the case that the new search is completely new, that you cannot use the third model because no one has ever looked for that search, we would use directly the models 1 and 2, the semantic models, to return all the results. And now let me show you how the results look like. This is the solution that how is implemented in the InfoJobs page. Two examples. You see that at the end of the page, above that, you will have the results of the actual keyword that you have searched, but after the search, the results of the actual search, you will find all these links that point towards the result pages of similar searches calculated using this model that I just presented. The good point here is that for the InfoJobs user is very useful to have these links because they don't have to think other job titles that they would be interested in. They can just follow our suggestions and go directly to other result pages that are useful for them. But apart from that, we don't have to lose the goal of this talk. It was improve the SEO. So apart from helping the user, we are increasing a lot our SEO because all these links create a super net of internal links between the different result pages of InfoJobs that increases a lot the SEO of our pages. As a result of this implementation, we end up with about an average of 9 links per search results page. And as a result, about 7,000 new pages have been indexed in the search engines. It's quite difficult to measure the impact of this because the web traffic is difficult to measure, and especially now we are living in an unseen situation. It's very difficult to see whether a new implementation has had good results or not, because to adapt this crisis, we implemented a lot of new things. It was quite difficult to differentiate the impact of each of the solutions. But we have been using, and that's why we went for a standard index, and we decided to measure the success of this project using the Systrix Visibility Index. That is an index that is a standard for measuring SEO success, and that is not, in theory, it is not sensitive to external factors. And we also could use it for both desktop and mobile versions of our website. Then, as a result of our solution, we measured that the Systrix Visibility Index increased about 6% from April, that it was when the solution was in production. And as a result of this increase in visibility, we estimated that the website traffic considerably increased in this month. I cannot give you numbers about the increase in website traffic because they are confidential. I am not allowed to give actual numbers, but what I can say is that we are very happy that this solution worked, and this was clearly a success. That's all from my part. Just remind you, as Clara told you at the beginning of the session, that we are in the InfoJobs team of machine learning. We are currently looking for a data scientist. So if you like what you just saw, you can just contact Clara, contact me, or look for the offer in InfoJobs and apply for it, because we will be happy to talk with you. Thank you very much. Now, if you have any question for me or for Ana, you can just write them and we will try to answer them.
I actually had a question. When you said that you combined the two models when you didn't have previous research from a user, and you combined the two models, how did you do the combination of both models? Did you just like concatenate the vectors, or?
We did no. What we did is we used the InfoJobs model, the second one, that was trained by us. Mm-hmm. and find the closer points. But for each prediction, for each point, we had like the distance and a score of the quality of the prediction. So if the quality was too low, we discarded this value. So we did something like this. Okay. Find the closest points using the two, and then using the score, decide whether they are important enough to be included in the results.
I see. Cool. Yeah, and in some cases, if when I've had these problems in the past, that you have an embedding that has not been trained with enough data, sometimes concatenating or appending the vectors, concatenating them, and to be trained in the model sometimes helps a bit because it grabs information from both places. But yeah, it's an interesting problem. Yeah.
Sure, it's something that we can also consider for future iterations. Yeah, about we have a question by Guillem Ke. Did you have to tackle multiple language like English, Spanish, or Catalan? If so, how did you handle it? Good point. InfoJobs, the most the more common language in InfoJobs is Spanish. So the pre-trained model, we used a Spanish model, or maybe it was multilingual, I don't remember. But what we do is that we usually start with Spanish, but then when we add real information, like in the second model that we used all the text in InfoJobs, then like naturally the current mixture of languages that are in our web page are fitted into the model, so the model starts to understand the different languages. But we usually start with Spanish because it's the most common by far language in our database. Okay, and someone else asked about whether this will be online. Well, we think that yes. Just keep in touch, and you will find when this is published. If there are no further questions, thank you very much. Thank you, Ana. Thank you, Clara, as well. And I hope you enjoyed this afternoon. Thank you.
Thank you, Didac, for inviting me.